We are approaching a point in time when humans will spend extended periods of time either in low or microgravity environments. So far, we have only experienced up to 374 days in the International Space Station. That is still within Earth's magnetic field, which protects against radiation. The first real long-term space exploration will be a permanent lunar base and a space station orbiting the Moon. The next challenge will be a crewed mission to Mars, which may take up to 3 years, where about half the time is spent in microgravity and exposure to space radiation. Welcome to Virtual Pathfinder channel. I make videos about imaging and especially astrophotography. If you're interested in exploring the universe with your camera, remember to subscribe to this channel. I use affordable equipment which can reach distant galaxies as well as detailed structures on the Moon. Let's have a look at the typical human health challenges associated with space exploration. Space travel presents a unique set of physiological and psychological hurdles that the human body is not naturally equipped to handle. NASA categorizes these into RIDGE. It's an acronym that stands for radiation, isolation, distance, gravity, and environments. Let's go through these issues one by one. First, we have the space radiation. It's invisible and highly penetrating. Space radiation is considered one of the most significant threats to long-term missions beyond Earth's magnetic field. There is a heightened risk for cancer due to the cumulative exposure to galactic cosmic rays and solar particles that significantly increases the lifetime risk of developing various cancers. The radiation can also harm the central nervous system. High-energy particles can damage neurons, potentially leading to cognitive decline and impaired motor function, or cause behavioral changes. It can also cause degenerative diseases. Radiation accelerates the development of cataracts and cardiovascular diseases like arteriosclerosis. Then there is the problem with gravity fields or microgravity. Living in a weightless environment causes deconditioning as the body adapts to not having to fight Earth gravity. That will lead to bone and muscle loss. Without weight-bearing stress, astronauts lose up to 2% of bone density per month and up to 20% of muscle mass on a 6-month mission. As an example, a one-way trip to Mars takes about 7 months, which would reduce bone mass by about 15% if no countermeasure is applied. That is near the level of osteoporosis. Our skeleton is continuously adapting to the environment. Cells called osteoclasts are breaking down the bone structures, while cells called osteoblasts are building up bone structures. Parts of the skeleton that are experiencing stress are strengthened, while other parts may be weakened. There's also a similar adaptation of the muscle mass where unused muscle fibers are broken down. Without countermeasures, a one-way trip to Mars would break down more than 20% of the muscle mass. If these effects are not mitigated, the astronauts will not be able to handle a return to Earth. I think even with gravitation, it is hard to stay in good shape. I'm usually doing long-distance running and a sprint every week, but if I take time off from exercise, I quickly lose that good shape. In space, the more limited space for exercise and the lack of stress from gravitation on bones and muscles, that is for sure a big challenge. Then there is the issue with the fluid shifts. Bodily fluids move towards the head, causing a puffy face syndrome, nasal congestion, and increased intracranial pressure. This is probably due to the body's adaptation to the resistance caused by Earth gravity to get blood to the upper parts of the body. In absence of gravity, that composition may lead to these effects. There is also vision problems. Spaceflight-associated neuroocular syndrome involves changes in eye shape and blurred vision, likely caused by the pressure of shifting fluids on the optical nerve. We have also cardiovascular changes, since the heart doesn't have to work as hard to pump blood upward, leading to a decrease in heart muscle size over time. Then we have issues related to isolation and confinement. The psychological toll of living in a small enclosed space with a limited number of people for months or even years is profound. There is an increased risk of depression, anxiety, and interpersonal friction between the crew members. You also have the sleep disorders due to a lack of natural light-dark cycles, known as circadian desynchronization. And then there's also noisy environments that can lead to chronic fatigue and reduced cognitive performance. Then we have issues related to hostile and closed environments. A spacecraft is a closed ecosystem where every variable from air quality to microbial growth must be strictly managed. These environments can create immune system changes. The immune system can become confused in space, while some parts may be overactive and others can be suppressed, allowing dormant viruses to reactivate. Microbial transfers is also an issue that needs to be considered. In a recycled air system, microbes are easily transferred between crew members and can potentially mutate and become more resistant. And finally, we have the issue with the distance from Earth. As missions venture further, for instance to Mars, distance becomes a health challenge in itself. In deep space, there is no emergency room nearby. There may be communication delays up to 20 minutes one way to Mars, which means that the crew must handle medical emergencies such as dental issues or surgeries without real-time help from Earth. I would assume that a 3-man crew, there would be at least one astronaut with a medical doctor's degree, and the others would probably need a thorough medical training as well. There is also, of course, supply limitations. Food and medicine have limited shelf lives. Ensuring nutrients remain stable and medications remain potent for over a 3-year mission is a major engineering hurdle. These issues I have mentioned are the main challenges for human space exploration. There are a number of countermeasures that can be applied to avoid the negative effects of space travel on human health. For instance, resistance training and usage of special treadmills are a way to avoid the degeneration of muscles and bone structures. The space fluid shifts where the body fluids tend to accumulate in the upper body can be evened out using lower body negative pressure that is performed using a special device that seals around the waist and creates a vacuum around the lower body, mimicking the effects of gravity. Thigh cuffs can also be used to trap the blood in the lower part of the body to avoid increased pressure on the brain. There's also ideas about creating artificial gravity, which is an interesting idea and that has been around for a long time. It was proposed by the German rocket engineer Wernher von Braun in 1952. There are some pros and cons with that, which I will get back to in a separate video. Protection from cosmic rays and solar flares is currently handled through passive shielding. Hydrogen-rich materials like polyethylene, which is a type of plastic, and water are excellent at absorbing radiation. Spacecraft walls are often lined with these materials. Storm shelters can also be used in the event of a solar particle event or a massive solar flare. Astronauts can retreat to the most heavily shielded area of the space station. That is often the sleeping quarters or area surrounded by water storage. Dosimetry can also be used to measure the level of exposure for each person of the crew. That is a way to measure the cumulative radiation exposure in real time. Then we have the psychological and environmental challenges that can be handled with several methods. By using circadian lighting, where light mimics the conditions on Earth with daylight and sunset light, the 24-hour sleep cycle can be maintained. Virtual reality can also create artificial environments that is typical on Earth, like forests and beaches. That is a way to reduce stress and the feelings of confinement. Communication using video calls with family and deliveries of personal items via cargo ships are also good for morale. Negative impact of space travel on bone health can be reduced to some extent with dietary supplements such as vitamin D and calcium. Medication to treat osteoporosis on Earth may be used to slow down the reduction of bone density. Then biomonitoring is necessary with regular blood tests and urine tests to monitor markers of stress, immune function, and nutrient levels to catch health issues before they become emergencies. All these countermeasures are necessary, but it will still be a challenge to bring a crew safely to Mars and back to Earth. That was all for this time. In the next video I will have a look at the ideas related to artificial gravity, where acceleration is used in different ways to create the same effect as gravity on board a space station or a spacecraft. If you're interested in space exploration and the coming lunar missions and the future crewed missions to Mars, remember to subscribe to this channel. See you in the next video. Until then, have a nice day.